Good afternoon, my name is Viktor and I want to present to you a report on a topic, test data processing used for structural fatigue life assessment. It consists from introduction, strain life fatigue analysis, test data obtaining and correcting, project development and setting, strain life fatigue calculation, conclusion and acknowledgements. An important engineering problem is to study the fatigue of materials and structural elements and predict the fatigue life of the structure. It makes possible to prevent fatigue failure of the material and ensure the safety and stability of engineering structure during the design life. Fatigue life calculation of varying load spectrum is a complex task. There are various approaches suggested to simplify the load spectrum into simple major and minor cycle. There are many different methods to definition estimated number of equivalent load cycles. The rainflow algorithms are one of the most popular counting methods used in fatigue and failure analysis in conjunction with lifetime estimation models. This method is also most often implemented in specialized software to analyze fatigue life. Modern software makes it possible to analyze the fatigue failure of structure under conditions of long-term action of loads that vary over time, opens up unique opportunities for designing and optimizing structures. The goal of the work is a fatigue life analysis using digital processing by encode Lytvynenko software tools of the test data obtained while studying in the stress-strain state of a wide spray field sprayer boom. The main source of input data for fatigue life analysis with the software is the previous results of structure finite element analysis or the results of field tests. In this work we use the test data that was obtained in the previous study, where the test data have been corrected to remove the data drift effect by tools of the encode Lytvynenko. The obtained in the time series data output file contains the stress, which is the function of time. For low cycle fatigue analysis, the strain is decisive, therefore it is necessary to convert the stress into strain. It is known that according to Hooke's law, within the limits of linear elastic strain stress is determined by the formula 1, where eta is strain and E is a modulus of elasticity. For steel, E is about 200,000 megapascal. The input data must be converted into microstrain, therefore we transform the data from the channels according to equation 2. The general view of interface encode Glyphworks is shown on the slide. There are main windows of the Glyphworks interface. First, Analysis Workspace, where the process is created. Second, Glyph Palette, glyphs available for processing. Third, Available Data, data that can be analyzed. Fourth, Diagnostics, list of process, error messages, etc. In Glyphworks, a process is defined as a combination of glyphs that define the data flow. A process typically starts with an input glyph to define the data to be processed. Additional glyphs define subsequent steps in the process for calculation, display, or writing output. To implement the procedure of the strain life fatigue calculation has been developed a detailed design containing the following glyphs: time series input, rainflow, arithmetic, strain life, histogram display, metadata display, and XY display. The obtained time series data output file was uploaded to the glyph time series input. These time series graphs are displayed in the central window of the glyph. This slide shows setting of the rainflow glyph properties. The settings of calculation glyph rainflow is left as default. The glyph rainflow output is connected with the XY display glyph input. The XY display glyph has been used to show the output data from rainflow glyph. The rainflow glyph counting results are correlation between of the load cycles number and stress. This slide shows setting of the arithmetic glyph properties. In the tab General in Selection Operator is selected the type of arithmetical operation equation. In section Equation Definition is written the parameter equation in accordance with equation 2. The strain life 1 glyph property dialog has two tabs, Advanced and Materials. The Advanced tab shows the glyph properties. The Mod property defines the type of calculation to be performed. In this case, we will be using the Damage mod, which performs a fatigue damage calculation. Under the Loading category, the Input Units property will set the units of the channels as UE, with the strain life glyph will interpret correctly as microstrain. The Materials tab window to choose the material is shown in the slide. Under the Material category, the material data source is by default as MXD database. We selected a material from the provided materials database file. Was selected hot rolled steel in the list, and this material name is now been entered the Advanced tab under Material name. The other properties in this glyph were left at their defaults. We use Materials Manager to review the material data parameters selected. For this is necessary to select the Materials Manager in the main menu. This slide shows a list of all available materials in this database. The default view of this set of materials is a tree view. The basic material properties of the selected hot-rolled steel are listed on the right side of the screen. There's static material properties like elastic modulus and tensile strength. In addition to static material properties, this database also contains material fatigue curves. The expanded contents under hot-rolled steel shows any fatigue properties assigned to this material. In this case, this material has a strain life curve. In addition to reviewing data, Materials Manager provides also the ability to add new, edit, delete existing materials data, and view a plot of the data. After completing the calculation, we can analyze the computation results, in particular to review the cyclic content by looking at the rainflow and damage histograms. At the top and bottom there are the damage and rainflow histograms respectively. The rainflow histogram shows the number of cycles counts on the vertical axis, plotted against those cycles' ranges and means. The largest number of cycles is seen on the left, where range is near zero. There's a small fatigue cycles. The biggest fatigue cycles are to the right. Fortunately, there are very few of these occurrences. This is often typical of strain gauge data, which may have many small cycles and a few large ones. The damage histogram shows a similar plot, but the vertical axis shows fatigue damage. The relationship between the number of cycles and fatigue life is defined by the material's fatigue curve. It is worth notice that all of those numerous small cycles seen in the rainflow histogram don't contribute any fatigue damage, and that most of the fatigue content comes from those few big cycles. We can also look at how damage accumulates over time. We can do this because the strain gauge data was measured against time, and the fatigue damage calculation tracks cycles. The XY display glyph displays time history, so when damage occurred in the time domain for each channel. A more thorough browse all the fatigue analysis results all of metadata display glyph. In this glyph under strain life results section, we can see fatigue results for each channel. We can see that the longest fatigue life is 92,670 times history repeats for channel number 1. These repeats mean repetitions of the entire input signal, with all the cycles that it contained. The shortest fatigue life is 3,981 time history repeats for channel number 4. The fatigue life in hours in this case is only about 484 hours. The fatigue life of field sprayers need to amount about 2,450 hours of operation, that amounts about 20,000 load cycles. In the current design, among the investigated hotspots are 1 over and 2 under-designed relative to this life target. The under-designed areas need some attention to improve their fatigue performance. We can use the strain life glyph's back calculation capabilities to assess how the stress should be increased or decreased to meet this target life. This is called a back calculation because we know the fatigue life and want to calculate what would normally be an input parameter, the stress level. For this we set the strain life glyph's properties as follows: mod, scale factor, and target life 20,000. The resultant table is shown on the bottom of the slide. Each channel's fatigue life is 20,000 repeats plus minus 1%. The last column is the back calculated scale factor that results in the target life. And so conclusion. The developed procedure of the strain life fatigue analysis under test data digital processing by ENCODE glyph4 software tools made it possible to calculate of the fatigue life for each of the 4 channels and to study about what causes fatigue cycles and damage by viewing them in the histogram and time domains. Analysis of the time history that display when damage occurred in the time domain for each channel made it possible to establish that the small fatigue cycles have the largest number but make small damage, while the biggest fatigue cycles have small number but the great damage spike, that is, the large strain magnitudes, contribute to fatigue damage. The results of the strain life fatigue calculation show that load cycles number of the channels 3 and 4 don't provide required meeting the 20,000 repeat durability targets or 2,450 hours. The channels 4 and 3 are needed as strain reduction of about 25% and 20% respectively are required to meet the needed durability targets. The channel 2 strain level completely provide required to meet the durability targets. The channel 1 strain level it is advisable to increase for about 23% to meet the target life. Acknowledgements. I'm very grateful to the company HBM Pransha and the team in Code for the possibility to use their software and for the information support. My special thanks to Lukasz Pinyak, account manager Pransha. Thank you for your attention.